Okay, so let me remind you what we were planning to do today. So we're going to work towards this this topic of looking at phases of electrons that are like the integer quantum Hall effect, but we'll be considering electrons with interactions. But nevertheless, we'll assume that these interactions are such that you remain in a short-range entangled state. Okay, so we defined what short-range entangled means last time, where the if you look at excitations in your system, you only have the excitations that you put in to begin with. For example, you don't get excitations with unusual statistics, and of course, we're only going to be talking about gap phases. Okay, so we're going to work towards this and show that the integer that people thought completely characterized these states has to be expanded, and there are two integers that are required to specify the state. Okay, and so we're going to do this by taking a bit of a detour. We're going to talk about phases of bosons. We'll assume that there are no fermions around, no electrons. And eventually the connection to electrons will be that these bosons will be something like the Cooper pairs, for example, of electrons, and they'll end up forming one of these topological phases. Okay, so we're going to talk about bosons, again in this short-range entangled phase. And instead of talking about this problem in generality, I'll focus on one particular case where you can sort of look at this problem in some detail. We'll look at this in two ways. One is sort of a microscopic construction, but not as microscopic as yesterday. So we did an example in 1D where we could have an exact solution and found a topological phase. Okay, but the microscopic construction I'll give you today won't be exact. It'll be more of a long wavelength effective theory. And I think it's good to have sort of both ways of approaching the problem. Sometimes you don't really want to focus only on exact solutions because we're really talking about properties of phases that are long distance properties and quite robust to changes in parameters and stuff like that. Okay, so this will give you some flavor of the kind of arguments you can make to sort of plausibility arguments that will kind of establish the existence of this phase, establish it at least for people like me who are who don't want sort of a mathematician's level of rigor. You'll be able to sort of make strong physical arguments by coupling these Luttinger liquids together in a special way. And we'll give an alternate derivation of a field theory, and of course the two should match, and they will. And we'll use this result to talk about this extension. Okay, and if I have time, we'll go to 3D. Okay, and again talk about phases of bosons with strong interactions, topological phases of bosons in 3 dimensions. Okay, and at least for me that was quite mysterious. What would the surface states of a 3-dimensional topological phase of bosons look like? So maybe we'll get to that today. If not, we'll do that in the final lecture. Okay, so the example we wanted to talk about had a pair of conserved species of bosons, but I first did a quick tutorial on Luttinger liquids. So let me again remind you of what was the main result. Okay, so we're going to couple these Luttinger liquids together. And we wrote this in a particular way. We said that the boson creation operator is essentially the exponential of a phase. Okay, so phi is the phase of the boson. Okay, and at the same time we introduce the theta variable, where this theta variable is defined in terms of the density of boson, the conjugate variable to the phase. Okay, but it was useful to actually take the derivative of theta, something that counts all the particles, all the bosons, say to the left of a particular point. Okay, and this we said is this theta, you can sort of think of it as a charge density wave phase, The derivative of theta is the charge density. And another way of thinking about it is if I look at the exponential of theta, this inserts a vortex. Okay, a vortex in space-time. So there's this nice duality between theta and phi. One is a particle, the other is a vortex. Okay, and the commutation relation between this theta and phi is just inherited from the number phase commutation relation. So let's say this is at x. Okay, and there's a Hamiltonian. We wrote on a simple Hamiltonian. Okay, this was like a charging energy. This is some stiffness for the boson phase. And then the important point was that if I wanted to get both the insulating and the superfluid phases, I needed to add this term, which allows for vortex tunneling. Okay? So there are two phases in this model. There's one phase where you can ignore this term if it's irrelevant. You simply look at the phase degrees of freedom. Okay, that's a superfluid. Okay, and the other phase is when you cannot ignore that lambda. Okay, let's say it becomes very large, and you end up pinning this theta at some particular value. Okay, that's the Mott insulator. Okay, just an insulator of bosons, one particle per site, for example, or some integer number of particles per site. It's got a unique ground state. Okay, so those are the two phases within this model. And if you wanted to write down a Lagrangian, okay, you can just convert this commutation relation. The way you usually do that, you want to write something like IP Q dot. And if you think of the coordinate as being phi, the momentum is just the gradient of this theta. Okay, up to some phases. Minus the Hamiltonian, of course. Yeah.
Can you explain why VI theta is a vortex?
Yeah, okay. So I kind of went over that quickly last time, but if you think of what a vortex does, so you want an operator that will take the phase. So let's say this is a space-time profile of your system, and I'm going to sort of label this in terms of the phase of this boson. So you have some phase like that. And you'd like to now write a vortex into this phase. Okay, and the way you do that is that you twist these things around so that along some line, the spin twists around by 2 pi. Okay, so the operator that will rotate a spin is simply you take the conjugate operator, that's n, and act on it with a particular angle. This operator will be a rotation of your phase by some angle theta. Okay, so now you want this rotation by an angle of 2 pi across this entire line. Okay, so what you would do is you'd apply this rotation operator at each point. Okay, so you'd integrate from some point x to infinity. You have the rotation operator, the number operator is going to do the rotation for you. And you multiply it by the angle you want to rotate, which is 2 pi in this particular case. Okay, so now you substitute for n. N is gradient of theta divided by 2 pi. Okay, so you cancel out that 2 pi's. Okay, and you do this integration. You throw away the constant at infinity, and you just get, maybe I've got a sign off, but essentially you just get that. Okay, so that's the vortex insertion operator, and it makes sense that you should have such terms in the Hamiltonian because that's what ends up giving you the insulating phase. Other questions? Okay, so what we're going to do now is we're going to take a set of these chains of Luttinger liquids, couple them together, and we're going to let these vortices condense. And if you just let the regular vortex condense, you'd get the regular insulator. but we're going to twist this vortex in some way so that once you condense it, you get this topological phase of bosons. Okay, so the setup is there are two species of bosons. Okay, you can think of some cold atom system, sodium and rubidium or something like that, two atoms that can't interconvert. So you have two conservation laws, one for each type of atom. Let me call them A and B. Okay, and the idea will be that we're going to try to write down a phase, a vortex condensate, okay, where, say, the vortices of A is bound to a B particle, and it's this composite object that's condensed. Okay, and you'll see it's symmetric between A and B. You can think of it as vortex of B and bound to an A particle. Okay, so so we'd like to do this, and we'll follow a very similar procedure as last time. But of course, we are in one higher dimension. So the things that we'll have to couple are actually tubes. Okay, so we have these tubes of these bosons. Let me draw one more. Okay, so and just to have two species, let me say that the two species live on alternate tubes. Okay. Tubes are wires, yeah. So we'll only allow hopping of particles between not nearest neighbor but second neighbor wires, right? Okay, and so if you were to think about a lattice in the other direction as well, we'll need that lattice to get an insulating phase on which the bosons can end up getting localized. So if you look at a vortex, let's say of the A degree of freedom, so the A bosons, if you like, live on these sites. Okay, this is the plaquette of the A bosons. So if you think of the vortices as lying in the center of the plaquettes, it's natural to think of them as lying over here somewhere. Okay, that's the vortex of the A particles. And so if you want a hopping of these vortices, which will eventually get them to condense, they're going to hop from, say, this site all the way here. Okay, that's again in the center of a plaquette of these A particles. Okay, and we'd like to make, when this vortex hops, we'd like it to also carry a charge of B. Okay, so when you do this vortex hopping, you'd better also take a charge of B if you want them to be bound together. Okay, so it's quite clear what we need to do. So let's start with just decoupled chains. Okay, so you have a bunch of these chains that are decoupled. So each of these is just a harmonic. So this gradient is just in one direction. So let me be explicit about that. So each chain, or wire if you like, okay, just some harmonic Hamiltonian. If this was all, this would be just decoupled superfluids of these bosons. Okay, and now we want to couple them in some way, so we can write down a coupling. Okay, so okay, so if this was the regular, just the usual vortex condensate, you would just write down just cosine of theta I. Okay, but now you want to do something more than that. So when a vortex hops from here to here, it creates a defect in the space-time configuration of this particular chain. Okay, so the place where it hops is the location of the vortex in this, according to this one-dimensional space-time picture, 1 plus 1D picture. So you always have this vortex insertion action, but now you also want to hop the bosons of these on the adjacent wires. So that's easy to write down. So it's just this. Okay, so just by itself, this the difference in these phases tells you that you hopped a boson from wire I minus 1 to I plus 1. But in the process, you also inserted a vortex. Okay, so you do this for every chain. It's like some modified vortex insertion operation. Okay, and there's one more thing you need to do, which is, you'll see in a minute, you need to stagger these phases. Okay, so the reason why this is somewhat approximate is we can just write down these terms for the long distance theory, but we're not quite sure what interactions at the level of the lattice will land you with just this term. Okay, but it's possible that by tuning couplings you could end up with just this term. Then we'll see we'll get into a gap phase, so then you have some latitude for changing couplings around and you'll stay in that phase. Okay, so the analysis from here on is very similar to what we did last time. What you do is you verify that all of these operators commute with one another. Okay, and yeah.
So if I just look at the isolated wire, your central charge in each eye is 2. You have one complex bosons or two real bosons, right? Is it the way I should think of it?
You have just you have one complex boson. Yeah.
So central charge is 2. The wire.
Central charge is 1. It's just a laryngeal liquid. So just take like an XY chain. Just take the XY model in 1D. That's a laryngeal liquid. Yeah. I mean, unless you want to combine both of these species and call it one chain, which is actually quite reasonable to do. But yeah, each is just a regular laryngeal liquid. Looks like this. Okay, so all of these terms commute. We'll take an example. Let's just take the first pair of terms. So you have phi 1 plus theta 2 minus phi 3 and phi 2. Okay, you have a cosine of this and a cosine of that. Those are the first two terms. And you can ask if this pair of fields commutes. Okay, and of course the problematic one is the ones that are common, number 2 and number 3. Okay, but you see that these will cancel out, and this will commute. So just like we did with the previous case with the spins, you have a similar situation over here. Okay, so you have this. You just use this commutation relation. Okay, so what this means is that all of these terms can be independently satisfied. They don't conflict with each other. And this is essentially like writing some modified term. Okay, like a theta tilde for every one of the chains. So you're guaranteed that if you had periodic boundary conditions, okay, so let's say you wrap this around on a cylinder in that direction and also in the other direction. Each of these will completely localize that particular laryngeal liquid in much the same way that this cosine localizes the laryngeal liquid and gives you a unique ground state for a Mott insulator. So you just have this particular field being set to some value, say 0, and that gives you a unique ground state. Okay, it's an insulator with a unique ground state and an energy gap. And at this level, it looks a lot like a Mott insulator. But you can really see the difference when you have open boundary conditions, okay, as usual. So this establishes that this is short-range entangled. There's no there are no exotic anion excitations or ground state degeneracy. So we are looking at a conventional phase in that sense, something with short-range entanglement. Okay, but you can still have topological properties. So if you look at the edge, Okay, so now let's say I don't have periodic boundary conditions. I terminate this at some point. So then the first term I have is the cosine of this, of that field. Okay, and as usual, I'm missing some particular term, the last one at the edge, which I would have had if I had periodic boundary conditions. I'm missing that term, and that gives me some dynamics at the edge. Okay, you don't completely clamp down on all the degrees of freedom. There's something that's under constrained at the edge, which is going to be our gapless edge mode. Okay, so we're going to look for a field that will commute with these terms. Okay, so that it isn't forced to be forced to some value by the cosine. So you want something that will commute with this last operator over here. So clearly the operator phi 1 itself commutes. Okay, so phi just commutes with phi. And you would have liked to have a conjugate operator like theta 1, let's say, to complete the description of the Lagrange liquid at the edge. But theta 1 doesn't quite work. Okay, to have theta 1, it doesn't commute with one of these constraints. There's a cosine of this term. So it means there's some conflict. And I'll really have to worry about how this is going to excite this particular term in the Hamiltonian. And it's not very clear what will happen. Okay, so we want a combination that will escape these constrained terms. So does anyone want to suggest? Yeah, so you just add phi 2 to that. I may be making some sign errors, but that's something we can fix later. Okay, so there's an additional field which comes along for the ride with this theta 1, and together this will commute with the cosine of this term. Okay, in other words, if I take this pair of dynamical fields, the Hamiltonian has nothing to say about them at this level. The cosines don't have anything to say about them. So you're just governed by the usual Lagrange liquid kind of Hamiltonian. Okay, so this will give you a gapless edge. Okay, which is just a Lagrange liquid actually. Okay, so we found a phase which is gapped in the bulk but is gapless at the edge, and the edge just looks like a 1D superfluid. Okay, there's some. Okay, the thing that makes it special, why this is not simply a one-dimensional system but really the edge of a topological phase, is that this gaplessness is protected by symmetry. Okay, if I just give you a one-dimensional superfluid, if I'm at the right filling, I assume that I can always change the filling, and then I can make it commensurate with the lattice, and I can always make it into a Mott insulating phase for a truly one-dimensional system. Right? There's always the option of making it insulating, whereas for this gapless edge, there is no such option. Okay? And the way you can see that is, if you wrote down a theory of this edge, in order to make it insulating, you'd like to add a cosine term, okay, which would pin these fields. Okay, so you can ask what kind of cosine terms could I add that's consistent with symmetry. So you could try adding cosine of phi 1. Okay, that would pin it and make it gapped. But phi 1 is actually the phase of the boson. So adding a term like cosine of phi 1 is sort of like adding a term which is just b dagger plus b. Okay, a term like that in the Hamiltonian. We know that term is not allowed because the boson number is conserved. Right? You can't just create and analyze bosons in your Hamiltonian because of this U1 symmetry, the conservation of species 1. So this is not allowed by the first U1 symmetry. Okay, usually what happens is that you can write a cosine of the second field. Okay, so you try to write down a cosine of this one, but this comes with the phase of the second species of boson. Okay, phi 2, that's our species B. So this is not allowed either for the same reason. Okay, it's violating the conservation law, one of these U1s that is the symmetry of your system. Okay, so basically there's no way by which you can gap this edge. Okay, so as long as you have the symmetry, your edge is going to be gapless. Okay, so this is a lot like the edge of a topological insulator, where the edge is gapless unless you break one of the protecting symmetries. This, in fact, is stronger because the symmetry you have over here is a pair of U1s. So U1s can't really be spontaneously broken in one dimension. In 1 plus 1 dimension, there's a Mermin-Wagner theorem tells you that you cannot have spontaneous symmetry breaking. You have a continuous symmetry. Okay, whereas the topological insulator is protected by time reversal symmetry, that's discrete, it can be spontaneously broken. Okay, but then we know that if it's spontaneously broken, you can look for that. You can look for the broken symmetry, and that always goes hand in hand with a gapped edge. Okay, so what you have in this, the edge of two-dimensional case, d equal to 2, you have a gapless edge. Or broken symmetry. Okay, so if I were to break by hand this U1 symmetry, allow for tunneling into some other superfluid, a proximity-induced tunneling to a superfluid of these atoms in another layer, for example, then I could add terms like this and gap out the edge. Okay, so with the symmetry, they're gapless. Without the symmetry, they can be gapped. Okay, so this is sometimes called symmetry-protected the topology is protected by the symmetry. So most of these short-range entangled states we'll talk about are of this kind. Not all, but there's one exception, but most of them are like this. Okay, without the symmetry, you just get the trivial phase. Okay, any questions about that? Yeah.
Can you explain why the commutator is 0? How does this come from the commutation relation for the field?
Oh, this one?
Yeah.
So you have a theta and a phi, and you have find a theta in the opposite order.
Okay.
So it's just like previously we had these two operators that anti-commuted individually, and then the product commuted.
Okay.
So you can, just verify that.
But the commutation relation that I have is for the x theta, not theta.
Yeah, so you can, convert that into commutation relation for theta by integrating both sides.
Oh, okay.
Okay, so so that was one way of looking at this phase. There's another way which is sort of complementary, which is to write on a field theory for this phase. Okay, and that's something we can,
So basically this edge, we cannot gap it anyway.
You can gap it if you decide to break the symmetry by hand. So the Hamiltonian as it is has the symmetry. But now let's say I break the symmetry by some external fields. Now physically what that means here is the symmetry is generated by the conservation of number. So you need some way of changing the number. So for example, you can get a big container of the fluid, which is superfluid, and have a Josephson link that allows you to tunnel into the edge. And that will break the symmetry for you by hand, because you'll have a Josephson tunneling from the edge to some other place, which will look like B dagger plus B. This is like Josephson tunneling. There's B dagger. There's another boson over here that ensures that the total number of particles is conserved, but that other boson is in a superfluid where you can replace it by a number. So if you break the symmetry by hand, then you can gap the edge. So it's either it's gapless or you have to break the symmetry. Yeah, so there's a refinement over here, which is, let's say the symmetry is not U1 but something discrete. Let's say it was Z2. It's possible for the edge to dynamically break that symmetry. Spontaneous symmetry breaking. But even then you get a degeneracy at the edge, which is, it can be all up or all down kind of degeneracy. So that's an indication of this topology. That's an equivalent way to diagnose it. There's never a unique state of the edge.
I can rephrase what you did in the Fermatic language. Essentially you have each wire has a left mover and a right mover, and you're just gapping out pairwise by doing backscattering between
That's right.
wires.
That's right.
So that's just the convention of the wire is description of
Yeah.
the quantum Hall effect.
Yeah. But of course, you can't quite do that here because the fermions are not physical. Right?
Well, I can think of it as that. I can interpret that in this way.
So here, you're only allowed to tunnel particles over here that are actually local operators. Right? When you tunnel between chains, you can't tunnel a fictitious particle between chains. You have to tunnel things like either the boson or this vortex. So the actual tunneling of fermions, you can always sort of fermionize this Luttinger liquid, but those fermions can't exist in the vacuum. They can't actually tunnel between chains. So there's, for example, if you try to think of what is the charge of that fermion, it'll be like square root of 2. It'll be some weird charge. Yeah, so it's important that these are really, bosons and, what you're tunneling are operators that are local in terms of the boson fields. Yeah.
So is this construction the construction for the other Z, and the non-chiral Z and the Z cross Z classification?
Yeah, we'll get to that, yeah.
We're not yet to the Z cross Z, right?
Not yet, yeah. Almost, but not yet. Because I want to do something, I want to derive the same result in a different way. Okay, which will be kind of useful, easier to generalize, then I don't have to do this coupled wire for every single case.
Instead of just thinking of fermions with like charge square root 2, could you think of some kind of a quasi-particle that was maybe some fermion but also like some vortex in that dual picture that complements this picture of bosons plus vortices, or is there some other way of picturing it?
Yeah, there are probably other ways of picturing it. But this is, the bosons it's important to distinguish like the local operators from some non-local operator you may define for some calculational convenience. So the only things that are local over here are the boson degrees of freedom. And that's important because when you look at what can hop between chains, you have a particle that goes into the vacuum and hops to the other chain. So that particle had better be a boson. Otherwise, it's not allowed in the vacuum. Right? You could have all kinds of weird excitations inside this chain if it's gapless. You can define all kinds of things. But they never leave the chain. So ultimately, you have to make sure. So what we're doing is we're displacing a vortex and we're hopping a boson. Both of those things are local. If you want to displace a vortex, you just change phases near the vortex and it'll move. And I hop the boson. So everything is done in terms of local degrees of freedom. And those are the only terms that can enter a Hamiltonian. Yeah. So I'm thinking of a system which has only bosons, like let's say sodium and rubidium or something like that. And we'll get to fermions. We'll add fermions to this, and we'll think of these bosons as some Cooper pairs eventually. But it's useful to just think of bosons for a minute. Okay, so let's write down a field theory for this, which is kind of a little more convenient to do stuff with. Okay, so we're going to write down an effective theory, and we're really interested in the topological properties of this phase. Okay, we're not interested in details at high energies. We're really interested in the low energy physics, which is really the topological properties. Okay, so let's try to write down a field theory. Okay, and this will be a little bit of hand waving, but we have something to compare the result to. Okay, so I think it's okay to have a bit of hand waving here. We can see if everything matches up, and if it does, that's a good sign. Okay, so what we are trying to do is write down a field theory for this kind of a vortex condensate. Okay, we're going to condense vortices of A bound to particle B. Okay, so or if you like the other way around, actually this is fine. Let's do it like this. Okay, so if I write down a Lagrangian for that. Okay, so if I have a vortex, what it does is that it gives your particles a phase. Okay, a phase of 2 pi going around. Okay, so you can implement that phase, that's like a Berry's phase or an Arnav-Bohm phase. You can implement that phase with a vector potential. Okay, so let me say I have some kind of an emergent vector potential, little a, that will end up giving the required phase to my particles. And the way I can do that is through this J dot A term. Okay, J dot A just gives you the Arnav-Bohm phase. I have this index which sort of generalizes it to the relativistic case. You have both the charge density, the density of particles, as well as the x and y components of the current. Okay, that's the 3 current. I sometimes use a notation like that, a vector notation, to be a little careful because this vector is actually a space-time vector, okay, not just a spatial vector. Okay, so this will allow us to implement this sort of Arnaud-Bohm phase. Okay, so this is the current of A, and this is some vector potential that keeps track of where the vortices are in this for these A particles.
So just to check the magnetic field in this case leading to the Arnaud-Bohm phase, which space is it in? Is it in?
It's in two dimensions. Yeah, it's in real space. That's right. Yeah, it's all in real space. It's not Berry's phase. Sorry, it's not momentum space, Berry's phase. Okay. Yeah, and these are interacting systems, so there's really no, clear-cut Brillouin zone kind of description for single particles. They're all interacting, so there's no band theory picture of this problem. Okay, so now this vector potential has to keep track of the vortices. So the curl of this vector potential. Okay, so I'll use this notation. Yes, I should have the indices up. Okay, so the curl of this vector potential is just where the vortices are, but we said the vortices are bound to these B particles. Okay, so all I need to know about the vortices is where the B particles are. Okay, and they follow them around. So this is simply the number density of B. In this more general notation, this is just the 3 current of the B particles. Okay, so if you specialize to the case mu equal to 0, that's the number density of B particles. That is the flux of this little a. Okay, so maybe we should call it a with a script B, which tells us that it's keeping track of the B particles. Okay, and I'll again use this 3 vector notation over here. So I'll write gradient as a 3 vector. There's a time derivative and there's a spatial derivative. Okay, so this in the 3 vector notation is curl of AB. Okay, and there's I'd like to put in a factor of 2 pi because I want a phase of 2 pi every time I see a vortex. Okay, so this is just 2 pi times JB. Okay, so I just traded my current of B for a vector potential that keeps track of what the current of B is doing. Okay, so we can rewrite this over here. So I replace, actually, let me leave it like this. So this is what this vector potential over here is. And you can do a similar thing for the current of A. You can replace that by a vector potential. So we have this current, okay, which is conserved. Okay, so in other words, if I were to take the divergence of this current, so if I did delta mu okay, so this is just telling you that there's a continuity equation that the number density of these A particles plus the 2 divergence of the currents okay, is 0. Okay, so in our 3 vector notation, this is just grad dot J is 0. That's the continuity equation. Okay, so you can solve this continuity equation. You have the divergence of some field being 0, so it's simply the curl of something else. Okay, let me call this AA. Okay, and again, just by convention, I'll use this factor of 1 over 2 pi to keep track of this. Okay, so I have a similar equation for both of these currents. I trade them for vector potentials that keeps track of the currents. Okay, so then if you just substitute that in the defective theory, okay, so now you have JA, which is this curl over here. Okay, it just looks like that. Okay, so this is a Chern-Simons okay, so we'll see that it describes the same edge as what we had over here. Okay, so the first thing to verify is that it's short-range entangled. Okay, and one simple way to see that is all of the phases that we're talking about over here involve phases of 2 pi. Okay, taking boson around the vortex and so on is all 2 pi phases. There are no fractional statistics appearing. Okay, so that's an indication that there's short-range entanglement. Okay, so another way to do it is we'll see later that if you write down a Chern-Simons theory with a proper normalization, which looks like this, a general Chern-Simons theory. Okay, the ground state degeneracy so if we have periodic boundary conditions, the number of ground states on the torus is simply the determinant of K. Okay, so this K will be some integer matrix, and the determinant of K will tell you how many ground states you have on the torus. Okay, so maybe I'll give you a reference for that. It'll take too long to do it over here. But in this particular case, the K matrix, if I write this out as a matrix, is simply the off-diagonal matrix, which looks like that. Okay, so you can verify that putting this into this form over here will give you 2 helpings of this cross term, and that will cancel the 4 pi to give you 2 pi. Okay, and obviously the determinant of this is just unity. Okay, so that is something that we'll use, keep using, and that's one of the very nice things of this Chern-Simons representation. It may look a little bit slick. It's you just write down a theory in terms of some vector potentials whose meaning is not very clear. It's somehow related to the currents. But once you have this theory, once you find the appropriate theory, any computation is really simple. Okay, and, yeah.
So can you explain again why that's the right Lagrangian, like from the just based on the picture of bosons hopping around vortices and things like that?
Yeah. So let's say I take a particle around a vortex. You make it encircle a vortex. You get a phase of 2 pi. So I want to model that phase. Okay, I want to write down a term that will keep track of that phase. So one way we know to do that is to imagine that your particle is moving in some electromagnetic field, and you set up the flux of the electromagnetic field to be exactly right to get that particular phase. Okay, and so that's this term over here, electrical current times some electromagnetic field. And you set up the flux to be exactly 2 pi times the number of vortices. But the number of vortices is simply the number of B bosons. That was
any kinetic term or anything else? J or whatever?
Yeah, so in general you have to add to these things like kinetic terms, but they won't change the universal physics of the state. So that's like asking what happens once I exit suppose I have some closed manifold, I have this theory, you have an energy gap, and then you can ask what excitation is above the gap. So those are details that we're not really interested in at the moment. When you go to the edge, it's a little more important because the edge is actually gapless. So adding things like kinetic terms becomes important to see the dynamics of the edge. But again, the topology of the edge, for example, this particular term in the Lagrangian, which is what controls what kind of edge you have, we'll be able to see that directly from this Chern-Simons term. It's this Hamiltonian that you don't see. Okay, but you can add higher derivative terms. You can add, for example, to this, you can add like a Maxwell term, which is like a curl of A squared. You can add cross terms and so on.
So it's probably the same question. Can you just take your original Hamiltonian and derive this from it by going to the old picture? Or you just guess the theory has the same boundary theory as your original one?
So, when you say you derive something, you're keeping track of some energetics, right? So that's like solving exactly a two-dimensional interacting problem. So, of course, we can't do that, right? You can't do that reliably. I mean, you can make scenarios. Certain parameter regime you'll be in this phase. That you can do, actually. You can argue that, for example, this picture I gave you, this coupled wire picture, you can rephrase that in terms of these vector potentials. And you'll see how, because we're going to go from the vector potentials to the edge. So going in the opposite direction is like taking this coupled wire construction and going to vector potentials. So there is some sort of derivation that you can give. But whether a particular Hamiltonian is in this phase or not, that's a really hard question. And you probably need numerics typically to figure that out. Yeah, so there is, as usual, you can think of different phases. And if you're in that phase, the philosophy is how do you, describe its essential properties. The things that make it a phase different from other phases. And those properties are really long-distance properties. It's not the detailed structure. That answer your question?
That's the second part. The way you wrote this Lagrangian is you knew the H theory, so you just continued it into...
Actually, I didn't quite do that. I tried to argue that we wanted to bind particles to vortices. Yeah. And that's how I arrived at this and these relations. So from this, we'll actually derive an edge theory, and we'll compare it with that, and we'll see it's the same thing.
In reality, you would do the other way around.
You mean if I already had this phase?
Yeah.
Well, there are two equivalent ways of describing the phase. It's whether you emphasize the topological bulk, which gives rise to the edge, or you want to emphasize the edge itself. And there are two equivalent ways of doing it. It's, two ways of viewing the same phase. In a way, this is more complete because from this you can derive the edge theory. But the edge is the only dynamical part in your system. So if I tell you the edge, you can actually, and you know that there's nothing else going on, that is, yeah. I mean, you need to know that nothing else is going on. But if you know, for example, it is short-range entangled, then you're done. Yeah.
If you remove the conservation statement for the particle number and current, would you still have short-range entanglement? Or?
Yeah, it would still be short-range entangled, but this would not be a topological phase then. That's a good question, actually. Okay. So this, by itself, doesn't necessarily guarantee a topological phase. So all we know that at this point is that it's short-range entangled. That is true whether or not you have the conservation laws. But now the question is whether this is an interesting phase. Are you describing a Mott insulator, something like that, or one of these topological phases? And for that, you need to know whether there are conservation laws. Okay, and the way in which you put in these conservation laws is we said that these are actually currents of some conserved quantities. Okay, so then you can, in principle, couple them to some external fields, which will keep track of these particles. Okay, and that's a useful theoretical device. If I want to keep track of an electrical charge, for example, I can couple it to an external electromagnetic field. Even if I don't really have that field, I can use that as a source term to actually figure out what's happening with my charge. Okay, so we can have a coupling to the A particles. Okay, and there's some vector potential over here, and a coupling to the B particles as well. Okay, and this only makes sense when you have a conservation law. Okay, that's when you can keep track of the number of particles and couple them to some external field. Okay, but we said that these J's, we can replace them with this, the little a's. So let me do that. So both of these terms. Okay, so this is the Lagrangian that we're going to analyze, and we've put in these external fields for convenience. Okay, for example, we'll be able to read off the Hall conductivity by having these fields in there. Okay, so we showed a short-range entangled. The question now is it topological? Okay, so we can answer that by looking at the edge, but let's first look at whether it has some quantized transport. Okay, and that's an equivalent way of characterizing the phase. If it has some quantized Hall effect, for example, then you know there's got to be edge states, and it's a topological phase.
A question.
Yeah.
What is the big
Yeah, so that's an external field. Yeah. So it'll be a number. Think of it as a number that doesn't fluctuate. And by varying this number, I can evaluate the partition function, and from that deduce, various physical properties. Okay, so let's do that. So we're thinking of writing down a partition function. Two of them. Yeah. Later we'll collapse it to a single one when I have a single conserved charge. Okay, so I imagine integrating this Lagrangian over these fluctuating fields, little a, that represent the motion of all of these particles. I get something that doesn't involve the little a anymore, but only involves these big A's. Okay, and that's like a response function. It tells you, okay, so let me write this as e to the I as effective of these big A's. Okay, and from this you can easily figure out things like the conductivity and the Hall conductivity. Yeah.
I just wanted to come back to Salon because there was something I didn't understand. When you compare it to the Chern-Simons theory, first you assume that in the Lagrange there, this term plus the symmetric is A and B.
Yeah.
And the second thing that just if I look at the factor for the term in A, B, AA, just because of the 1/4 pi in Chern-Simons and 1/2 pi in the Lagrange, I find K is 0, 2, 2, 0, and not 0, 1, 1, 0.
No, actually it is 0, 1, 1, 0. There are two helpings of this cross term. So, okay, maybe your first question I didn't answer properly. This is the only term that we have. And it's actually symmetric in A and B. So that's a nice exercise to figure out, to show that this is symmetric in A and B. You might think there's a sign, but there's no sign. You can switch A and B and you have still the plus sign. Okay, so what is this as effective? You just have a quadratic theory. So it's a Gaussian integral. That's the one integral we can actually do. So let's do that. And when you integrate out over these little a fields, you can just extremize with respect to those fields and substitute that back in this Lagrangian. Okay. That's how you'll evaluate this as effective. Okay, extremize with respect to little a, b, for example. And what this will give you is essentially that AA is okay, I'm being a little sloppy over here. There are all kinds of curls that only project out the transverse piece. But essentially this is what you get from extremizing. You put that back. I guess there's a minus sign. Sorry. You put that back in that Lagrangian, and you get as effective. Okay, so that'll tell you what the response of this is if I apply some external fields. Okay, so let's say I were to apply on B particles, right? Okay, so imagine you, for example, you tilt this in such a way, maybe you have some interaction, some light field that only interacts with the B particle, and make them go in one direction. Apply a force on the B particles, and we'd like to see what happens. Okay, because of that. Okay, so we'd like to know what the currents are. Okay, and the important thing is going to be the A current. Okay, and of course that is simply the the term that's coupled to the vector potential AA. Okay, that's the current. That's what couples to AA. Can you see that what couples to AA is this curl over here? Okay, so if you had some flux or some field on this AB particles, there would be some non-zero value for this external field. Okay, so if you actually write out the components, the zeroth component is the effective magnetic field, and the x and y components are minus EY, some sort of script. Okay, and all of these are acting on this B particles. Let me put it up there.
I have a question.
Yeah.
When you just take the fixed point of the Lagrangian, is this somehow a zeroth order approximation in diagrams?
So this is a quadratic theory.
Yes.
So, it's like harmonic oscillator where all approximations are actually exact. Right, so the saddle point is exact. You can just do the integral if you like, and it'll give you this. This is how I do this is my way of doing Gaussian integrals.
Okay.
Yeah. But, you can just invert this matrix and get it, and you'll get the same answer. Okay, so if you look at the currents that, so Jx, for example, of the A particle will be 1 over 2 pi times Ey, okay, acting on the B particle, and Jy acting on of A is minus 1 over 2 pi times electric field in the x direction. Okay, so essentially this is a Hall conductance, right? So you have a Hall conductance, but it's kind of a crossed Hall conductance. It's sigma xy, but it's between A and B. Okay, it's a little bit like a quantum spin Hall response. Okay, you apply an electric field and you get a spin current. Okay, you apply an electric field on one of the U1s, you get the other U1 in the transverse direction. Okay, and this sigma xy is 1 over 2 pi. Okay, so we've used some units over here. We used units where the charges are all 1. So in fact, I could have some charges Q1 and Q2 corresponding to the two of them. I've set them equal to 1. I've also set h bar equal to 1. Okay, so in these units, 2 pi is actually h. So this is, if I were to write it more like a Hall conductance, this would be a product of charges divided by h. Okay, it's like E squared over h, but these are two different charges in general. Okay, and it's a cross term, but it's quantized. Okay, so you have a quantized cross Hall response, which tells you that this is a topological phase. Okay, it's not a boring Morton-Slater. There's something interesting about it because it has this quantized response. Okay, of course, to be able to define this response, you need that these charges are conserved. If you are a superfluid of one of these charges, then you can define this response. Yeah. So think of them as being some charge associated with these bosons. So instead of having unity over here, I could have had a Q. You can set them to 1 if you like, but I want to make it appear more like E squared over h. Yeah, that's right. Yeah. Maybe I should call them QA and QB. I think that's probably better notation. Yeah. Okay, so that's the Hall response, which tells you this is a topological phase. Okay, so finally, let's make this completely clear and show that you get also this edge state, okay, that we had before. Okay, in fact, having this sort of Hall response already tells you this is the relevant edge state, but let's just derive that for just to be pedagogical. Okay, so we want to go from some effective Chern-Simons theory to the edge states. Okay, and I think you've probably seen this in one of the previous lectures. I think I saw Joel Moore had some notes in his lecture notes which talked about this. Okay, so do you want me to go over that again? How to go from the Chern-Simons theory to the edge states?
Sure.
Okay. At least one person, yeah. That's the wrong question. Yeah. Okay, so what we want to do is, so let me just stick with this part of the Lagrangian for a moment. And what we want to do is we want to go to, think of some system that has an edge, let's say along the y direction. Okay, it ends somewhere. Okay, so this thing is gapped in the bulk. The only gapless excitations will be at the edge. We want to find the effective theory of the edge. Okay, so to do that, let's look at this theory over here. We'll come back later and figure out what is charged and all that. Look at this theory over here, and so let me separate out those terms. Okay, so there are two kinds of terms. Ones that have a time derivative over here. Okay, those give you some sort of dynamics. And then there are other terms which don't have any time derivative. And those are like a constraint. Right? So the terms that have a time derivative is something like ABX, time derivative AAY. I guess this comes with a minus sign. Okay, and then there's another one which is okay, that's the dynamics term. Okay, and the constraint terms are ones like AB0, dx, AA, y, and okay, so what these constraint terms do is, for example, if I integrate out A0B, that will simply impose a constraint that your, yes, there are other terms, sorry. Okay, and I guess I can write this as yeah, so that's pretty clear. There's this constraint that tells you that the fluxes over here, the spatial fluxes, are both zero. Okay, so that's kind of what Chern-Simons does. It sort of clamps down on the fluctuations of charges or flux because they're tied to each other. Okay, so these sort of two curls have to be zero, which simply means that these vector potentials have to be gradients. Okay, so you have that. You can solve the constraint. I'm sorry, maybe I have A then. Okay, so it tells you that these AIs, the spatial ones, are the derivatives of some fields, some scalar fields, let me call them phases, phi, A and B. Okay, so I get two phase fields. That's good news because we want two phase fields at the edge. Okay, and these vector potentials are simply spatial derivatives of these phase fields, the spatial vector potentials. Okay, so you can substitute that into the part of the Lagrangian that's surviving this integration, which is the ones that don't have the A0 in them. Okay, so actually I want to go to the action, which is the integral dx dt py times L. Okay, so there's this integration that we have to do. It's 1 over 2 pi. Okay, that's what you need. That's what you have at the edge. Okay, now we're going to integrate it over y. So we'd like to write this as a total derivative on y. Okay, so then it'll be easy to do that integration. Okay, so let me write it as dy. Okay, so that's one term. And then there's a pair of terms that you get by acting this on this field and this term that was hanging around, and they actually cancel. Okay, so maybe I'll show you they cancel, because that's something that I keep forgetting when I try to rederive this.
Could you just say once more why you said that the gradients, the spatial gradients have to be
these objects? Okay, so you have an integration over all of these little a fields, and these A0 fields, they don't have time derivatives, of course. Okay, because this comes in the form of a triple product. So if you reserve the time derivative for in the derivative, it doesn't appear on the fields. So A0 doesn't have any dynamics, so it's like a constrained field. It's like a Lagrange multiplier. So you can just integrate out the field A0 when you do this functional integral. And what it does is it just forces these things to be 0. Okay, so there is an additional term over here, plus 1 over 2 pi. Okay, so and that's this term that came down. Okay, and these two terms cancel because you can do an integration by parts and take this x from acting on this field to that field. Okay, you do that, you get a minus sign, these cancel. So the only term you're left with is this one, and it's conveniently within a total derivative. So you can integrate with respect to y, okay, dy, and you just get the value of this field at the edge. Okay, and it's just a one-dimensional problem after that. So this one, if I okay, so you just get, maybe I should call this the edge. It's only an integral over one spatial dimension now. Okay, and then of course this is just the topological part, so there is some edge Hamiltonian, which depends on these fields phi, okay, which will actually give some dynamics to this. Okay, and this you only get if you add additional terms to the original Hamiltonian, so it's not purely a topological theory. Okay, but the key is this, what tells you the commutation relations between the edge fields, and that's exactly what you have for this Lagrange liquid. Okay, so the 1 over 2 pi is important. This normalization is fixed by knowing what the local operators are. Okay, you're not allowed to rescale these fields phi because there's a meaning to e to the I phi. Okay, that creates a boson, for example. So you're not allowed to rescale these fields. So this overall normalization controls the properties of these theories. Okay, and you can actually figure out that this phi under one of the U1 rotations will be transformed exactly like these fields. Okay, so we leave that as an exercise that one of the U1s will change one of the phis, the other U1 will change the other phi. Okay, I think it's U1A that changes phi B and U1B that changes phi A. Okay, so you can identify phi B with phi 1 and this phi A with this one. Okay, so you get the edge theory, from the same edge theory as that. Okay, so we're almost there. Okay, so eventually we're going to be interested in electrons. Okay, and electrons don't have a pair of U1s, they just have a single U1, total charge. Okay, so this was a useful device to get to this theory, but now we'd like to say that there's a single U1, that instead of having two species of bosons, let's say the two species of bosons are actually the same. Okay, so I have this topology, and then I can imagine some process which begins to allow for interconversion of these bosons. Okay, so that I have a single U1, and both of these individual U1s are the same. Okay, so I want to reduce my symmetry from U1 cross U1 to just U1. Okay, but the way I do it is not by breaking one of the U1s. I say that both of them are identified okay, so both of them are going to be identified with a single charge now. Okay. So then do I continue to have a topological theory or not? That's the question. Okay, and actually it's easy to see that you do, because now you have this phi 1 and phi 2, and they both transform under the same U1. Okay, so they're both charged on the same U1, and again, you can argue that you cannot gap out this edge. You can't write cosine of phi 1, and you can't write cosine of this field because this is also charged. Okay, but we'll also see that it has a quantized Hall conductance. And now because I just have one species, this is the regular Hall conductance. It's not some cross response, and we'd like to know what is the value of this Hall conductance. Okay, so this is a short-range entangled state of bosons. It's kind of like integer quantum Hall, but for bosons. Okay, and you might have guessed that the Hall conductance is an integer. Right, so we'll see it's an integer, but we'll also say it's not any integer. Okay, there's an additional constraint that you get for bosons that you can see from this theory. Okay, so now instead of having these two vector potentials, I'm going to set them equal to the same vector potential A. Okay, that's the single U1 that I have. That's going to be the electrical charge, and these bosons are ultimately going to be Cooper pairs. Okay, so I get just a single A. Okay, and now I'd like to find S effective with just the vector potential included. Yeah. Yeah, that's a good question. But so these are some internal fields that will retain the topology of my state. And the way in which I'm doing the symmetry breaking is by saying that I can only invoke the single field, the single external field. Okay, so that's a little unsatisfying because it seems like you're still keeping track of some A and B labels that don't really make sense. But within this sort of abelian kind of theory, simple abelian theory where you just have quadratic Lagrangians, this is a device that you have to kind of stick with. And if you like, what you can do at the end is go to the edge and allow for conversion of this A into B. Okay, so that's really like some tunneling event where you allow for flux of A to become flux of B. So in the bulk, it's like a monopole event. It's a monopole that gets rid of flux in A and puts it into flux of B. That's really hard to do in this theory, to analyze that. But it's really easy to analyze at the edge. You allow for example, this phi to convert into this other phi 2. But you can check that doesn't gap out the edge, because just by this argument that you still have some symmetry that blocks both the cosines. But that's a really good question, that to retain the topology, you have to somehow still think of two components, although the components can interconvert. In some cases, we actually understand why we need to do this in more detail. Like there's some cases where you get fermions, And for certain flux configurations, you get fermions, and you want to have two whirl lines that stick to each other so that you can tell if it's twisting around. So it's sort of a poor man's way of doing getting access to these topological phases. Yeah.
So since the state that you get for the system with the symmetry U1 cos U1, now that you break the symmetry, so the state that you get is a symmetry protected topological state, right? And now you break the symmetry.
You break it partially, yeah.
Shouldn't there be let's say a gap closing when you go from one phase to the other?
No, so once you change the symmetry, you can't really compare phases which have two different symmetries. Okay. Right? You're explicitly breaking the symmetry. You're actually putting in a field that will make this into a single U1.
Well, but here you can see this as a limit where I just drive AA and AB be equal. So
yeah.
You can continuously do that, right? So in this sense...
Yeah, so if you like, you can say that you have the symmetry, you're just going to explore a certain response function where you have the same coupling to both A and B.
Okay.
Right? If you like, you can say that. Okay. But ultimately, it won't even matter that we have these separate conservation laws. You can break that. You need that the total charge is conserved. That's important, but not that individual ones are. For this, the properties we'll talk about now. Okay, so what's the effective theory for this one? Okay, so you do the same minimization procedure.
That's just a technical question.
Yeah.
Why do you say that it's important to keep A and B in the system? If I just take that formula, erase them, and add two last terms, will something go wrong?
Yeah.
What's going to go wrong?
So that's not a phase of bosons. If I erase these, if I have a single component A, that's actually a theory of the fermionic integer quantum Hall effect.
How will it know about if this is A and B?
Well, if you look at the K matrix that we're talking about, in this case, the K matrix is 0, 1, 1, 0, when you have two components. And in the other case, the K matrix is just 1. They're different.
So you will have just K matrix in this form.
Say again?
Are you going to have K matrix?
I'm going to keep this matrix, yeah. This is going to be important. This is not a theory of bosons. We can talk about that. And this is actually key, that you'll see that the Hall conductance is not the same as an integer quantum Hall.
It's twice more,
Yeah, it's twice more, yeah. Okay, so let's do this integration, and you guys can do it. And what you get is you set these A's to be equal to A, and you get again the same thing that you had before, but now it's a single field. Okay, we had before AA times curl of AB, but now it's just single vector potential. Okay, and if you ask what is the Hall current now, there's just one response, of course. There's just a J, and that is going to be minus 1 over 2 pi, the variation of this action with respect to A. Okay, but there are both of these are identical, so there are two helpings of this. Okay, so you get this all-important 2. Okay, so so this tells you that the Hall effect, sigma xy, is 1 over 2 pi times 2. Okay, so we didn't include the charge again, so let's include the charge. So 2 pi is h in our units, and this is q. Okay, so it's 2 times what you would have expected from fermions. If I had the same unit charge between the fermions and the bosons, then this would be 2 times larger. Okay, and we know that we can add phases. We talked about that in the first class. So actually you can have any integer times this. Okay, so I can just take copies of this and stack them up. I'll get integer times this one. Okay, so now for a moment, think of them as not just some bosons, but Cooper pairs. Okay, so then Q is 2 times E. Okay, so then sigma xy, a factor of 4, so it's 8 E squared over H times M. 8M, I guess. Yeah.
So if I return the double trans you have here with the same way to the so suppose that I write sums and difference of the AA and AB.
Right.
And plug in A up and A down.
Right.
So I can rewrite this as a K matrix 1 minus 1, just like the
Right, right.
But then the A field is only coupled to say the upstream.
Right.
So you can interpret this as a quantum Hall effect where your
Yeah.
vector potential only couples to the
Right movers. Yeah, yeah.
Now the factor of 2, then it's a choice, right? Because I think it's a normalization of, this thing is twice the A plus B is something like maybe 1/2 of the middle A up. So
the way it works out there is the factor of 2 comes out because these fermions that you're writing down, these weird fermions, they actually carry square root of 2 charge in terms of the boson charge. So of course they're not physical fermions. There's some. So then you get E squared over H and you get 2 times, Q squared over H times square root 2 squared.
But then in that language there's something funny, right? Break the symmetry. My vector potential only couples to the up spins, but then I don't interpret this as a Hall conductance of Cooper pairs instead of just a Hall conductance of the up spins because the down spins don't couple.
That's not really spin, right? The plus and minus combination is not really spin. It's
No, you can call it.
Yeah. So what it actually means is that if I look at this Luttinger liquid, I could fermionize it into a right and left mover, and only the right mover carries charge, and the left mover is neutral. That's one way to interpret it. It's not a very good way of interpreting it, because the fermion is not real. I mean, it's some square root 2 charge. So you may as well just think of it as a Luttinger liquid. But you could, if you want, do it that way. And that's related to this combination that you talked about. So what I want to do over here is I want to only use fields that are physical in some sense. That when I go to the bosonized edge theory, the bosonic fields that I get, I can exponentiate them and call them some local operator. You can't do that with the sum and difference of these fields with some square root of 2 normalization. That's some weird fermion or some weird particle. Yeah.
Why are you so opposed to things with square root 2 charge?
It's sort of good to keep track of what is local in your theory.
What does that charge do to non-local?
Well, in your spectrum, there is no square root 2 charge, right? All the excitations in your spectrum are integer charges. So if you can make a square root 2 charge with some really weird operator, but it will never appear in a Hamiltonian. So if you just keep all the local operators, keep track of what is local, you'll know how to write a Hamiltonian. Okay, so we're almost there to talk about this second integer for our integer quantum Hall state. And it's really just this, yeah.
You probably answered the question, but I didn't understand. Why are there two kinds of particles in the system?
So that's a route to getting to this. So part of it is, you want a description of this topological phase that's simple, right? You want like an abelian field theory. So it's not that you're just asking for a description of the phase. I want something that I can present on the board in 20 minutes, right? Or you can work with easily. So to do that, you pay a price. And the price is that you have to keep track of these fictitious degrees of freedoms A and B, even though they may not be a conservation law. Now, often there's some good physical reason for that you're trying to capture some topology that's not very easy to capture with just an abelian Chern-Simons theory. You may want to have like discrete fields, for example. Sometimes we don't even have a continuous symmetry. You can do all of this for, let's say, Z2 symmetry, where also there's a topological phase. But you can sort of fake it by using this continuum theory with the continuous symmetry and then break it down to Z2. If you like, you can say that there's some spontaneous symmetry breaking. So there is some, at the Hamiltonian level, there's still some, you still have some notion of two species, but it's spontaneously broken. You have Goldstone modes. And
but in the physical system which is described like the
yeah.
There is one kind of particle.
That's right.
Just a trick to...
That's right, yeah. You can think of two layers maybe. Sometimes you can think of Cooper pairs can be in two different orbitals or two layers. You get into this phase and then you can perturb it. Right? Once you're in the phase, it's a gap phase. It doesn't require this additional symmetry, and you can perturb it with symmetry breaking fields. and you're guaranteed that you'll still be in the same phase as long as the symmetry is not important. Right? So that's sort of the philosophy. So you get into it on some simple route, and then you make sure that perturbations are innocuous. Yeah.
What prevents the bosons from forming a unit Hall conductance?
Yeah, good question. So you can show that if you have unit Hall conductance, that has topological order, in the sense that you can make an excitation which is a fermion. So if you do this Laughlin flux threading argument, you can show that the bound state of 2 pi flux and whatever charge it sucks in is actually a fermion. And maybe it was implicit in what Andre was doing the other day, yesterday. But that thing is actually a fermion. And you can also see it from this K matrix description. That a theory built out of bosons should always have even lengths. So this Hall conductance is like some length in this of vectors using this metric, this K metric. Okay, so let me get to this point because we're almost there. Yeah. Okay.
Play the same game, but start with not product of U1s, but U2.
Yeah.
Will I get different phases?
So it's hard to implement non-abelian symmetries within this language. It's much more natural to just do the abelian symmetries because non-abelian is, this is sort of keeping track of numbers of particles. And non-abelian, you may need something more complicated. You can sometimes fake it. You can break an SU2 down to something smaller, like Z2 times a U1. That'll be good enough. And that's something you can do actually within this K matrix thing. But the most general non-abelian symmetry, it may be hard to do. Luckily, we don't. SU2 is the only non-abelian symmetry we're interested in, and we have ways of doing it. Yeah.
But as a matter of principle, if I start with the same, just one array of layers, but more, and I use non-abelian mobilization, then I can probably match the non-abelian transaction with the H theory.
Yeah, maybe you could do it. I couldn't. But yeah. Yeah, so abelian is about as far as I can do, and it's nice that you can get all these phases that way. Okay, so how do you? So we know that with free fermions we have integer quantum Hall effect. So let's try to characterize that and see how it could be extended. Okay, so now we're going back to electrons. Okay, but we retain the short-range entanglement. Okay, so no fractional quantum Hall phases. So free fermion, so let's just analyze this a little more closely. So free fermions, of course, we know that there's an edge state which is a free, a chiral edge mode, but of free fermions. So if you look at sigma xy, you have some integer times E squared over H. Okay, but also this is a chiral edge mode. Okay, so if you look at thermal conductance, kappa xy, okay, which simply counts how many chiral edge modes you have. So the count for one single chiral edge mode is going to be 1. That's my normalization. And in fact, this is something like that, I think. There's some combination of natural constants, which is like this E squared over H. Okay? But I'm going to set this equal to 1 from now on, so I don't have to write all of this. I'm going to set E squared over H also to 1, and I'm going to drop this T. This is actually the temperature. Kappa over T is like the response function. Okay, so for free fermions, we have two conditions. N is integer, and N is equal to C. Okay, that's what always comes out of these free fermion theories. Okay, so this is like a Wiedemann-Franz law. Thermal conductance is equal to the electrical conductance in the Hall channels. These are both in the Hall channels. And that's something that has to be obeyed by free fermions. Okay, so the question is, how can this change once I have interactions? Okay, so one natural guess you might try is, maybe this is not an integer anymore. Okay, but you can prove that as soon as this is not an integer, the Hall conductance is not an integer. Actually, Laughlin made this argument many years back. That it means that there are fractionally charged excitations in your system. Okay, so that can't be short-range entangled. You've got a fractionalized excitation, and it better be integer if you want short-range entanglement. Okay, so you cannot mess with this. Just leave this as it is. I guess let's continue to use that in the interacting case. Okay, but it turns out that you can fiddle with this one. Okay, with interactions, it could be that n is an integer, but n is not equal to the thermal Hall conductance. Okay, and we have an example over here. We can take, say, some integer quantum Hall effect of electrons, but put the Cooper pairs in one of these topological phases. Okay, so then your n would go to n plus 8 times m. This is a new Hall conductance. Okay, so you would modify the sigma xy, but this particular theory has a non-chiral edge. And the way we know it has a non-chiral edge is once you break the symmetry, there's no edge, there's a gapped edge. Okay, whereas a chiral edge, where you have excitations moving in one direction, even if you break symmetry, these are going to be stable. Okay, another way to say it, this is just a Luttinger liquid, right? The edge is just a Luttinger liquid, just has some weird transformation properties under the symmetry. Okay, Luttinger liquid is non-chiral, just a 1D Luttinger liquid of 1D chain. So in this process, you don't change C. Okay, C stays the same. Okay, so with interactions, okay, so this was free fermions. With interactions, okay, n is still integer. Okay, but n minus C can be 8 times an integer. Okay, and that m is the additional z. So you are now classified by 2 integers, the n and the m, if you like. So how much time do I have, Claudio? Am I?
Could you wrap up for this action?
Okay, so maybe I'll make one last observation before we switch off, which is, so we did this by adding this Cooper pair topological insulator, but there's another thing that you could see, which is it's possible to have, so the Cooper pair topological insulator had C equal to 0 and sigma xy equal to 8m. Right. So let's call it the bosonic integer quantum Hall effect had sigma xy equals to 8 times m and kappa xy equal to 0. Yeah, so that's the argument that it's a non-chiral edge. So kappa xy is just the chiral central charge. Yeah, so maybe I should have said that. Yeah, it just measures how many right movers you have relative to left movers. It doesn't care about symmetry because it's just talking about energy conservation. Right? It's a transport of energy. Okay, so that's this one. But you could imagine adding to this 8 copies of the integer quantum Hall effect of fermions and cancelling off the sigma xy. Okay, so you could get sigma xy equal to 0 and kappa xy equal to 8 times m. Okay, and we'll talk more about the state. It's a logical consequence. It's called the E8 state. Okay, and this 8 over here is related to the 8 that Andre talked about yesterday. That when you have 8 copies of the integer quantum Hall effect, the flux becomes trivial. Okay, it doesn't have any topological spin. And then you can condense the flux and you can simply get into a bosonic theory, which has multiples of 8 edge states. Okay, so we'll talk more about that later. And using these two, so this is sort of the bosonic analog of a px plus ipy superconductor. Okay, so this state has chiral edge states, so it doesn't need any symmetry to be protected. Okay, this is the only short-range entangled state of bosons that we'll talk about, which is protected in the absence of symmetry. Okay, so if it was not for this state, we could have simply called everything, all of these topological phases with short-range entanglement, we could have called them all SPT, symmetry-protected topological phases. But this doesn't need a symmetry. Okay, and it's important to include that in this discussion because it turns out if you don't do this, you miss some states in 3D. Okay, so this is the bosonic analog of a P plus IP superconductor. You have no symmetry, but still you have edge states. And this is the bosonic analog of the integer quantum Hall effect. Okay, and we'll see that with these two, we can actually say quite a lot about 3D states. Okay, but that we'll do tomorrow. Yeah.
Can you write an effect selection term just like AZA for the second response?
For this kappa? Yeah, so, because this is energy transport, you can ask what is the vector potential it couples to. So we know that energy actually couples to the metric. Right? So you can write down some gravitational Chern-Simons term that is the equivalent of this response function. Now, that's why I'm not writing it. Right? It's,
I set you up. If you write this term, then you don't get this from gravitational Chern-Simons.
With free fermions, you won't get this. But with interacting phases, if you demand that you have short-range entanglement and ask what kind of response you can get, you'll end up finding this, presumably. Yeah.
So the K matrix for your edge theory, which has n plus 8n, so that's how it will have n chiral modes plus 8 Kramers doublet. So
Sorry, say again. This one.
Yeah, when you go to n plus 8n.
Huh.
So your K matrix will have a set of chiral modes, but you will have also Kramers pairs.
They're not Kramer's pairs, but they're the 0, 1, 1, 0 kind of blocks. Yeah. That's right. Yeah.
With determinant form.
Yeah.
So the fermionic integer Van effect is n equals to c, right?
Yeah. The free fermion one is n equal to c.